In the last section, we were learning how to use Coulomb's law to calculate the electrostatic force between two charged particles. Well, now we're going to just increase that and we're going to have multiple charged particles. And the key to doing all this is that we're just going to be focusing on one particular charge at a time. We're going to break this example down into 2 different days worth of lessons just to make sure that we're not going so fast that you guys end up getting lost. In today's video, we're only going to look at part 1 of exercise or of example problem 13.2. He starts off, he shows you in the explanation that he does, he has 3 particles that are not in a straight line, but we're going to practice doing this first with 3 particles that are in a straight line just to make the math a little bit easier because we want to make sure that we're understanding the concept behind it. So example 13.2, we've got 3 charged particles and they're arranged according to the diagram. They're on page 435. And so the question is asking is, what is the total instantaneous electrostatic force exerted on the negative 3.4 millicoulomb particle? So let's kind of break this down for a second here. First of all, he says, what is the instantaneous electrostatic force? The charge or the force is just going to be instantaneous because if these charges are free to move and they have a force being exerted on them, then they are going to immediately start moving towards one another. So if I have a positive charge here and a negative charge here and they aren't attached, they're not tied down in any way, they will start moving towards each other. Well, if you recall the equation for Coulomb's law, there's a distance in there. The distance is on the bottom. And we said that the closer they get together, the stronger the force becomes. So as soon as those charges start to move, the force is going to be different. So that's why we have to specify that this is an instantaneous force. It's only good for the moment in time when they are at the given distances, because after that they're going to move and the force is going to change. Okay, so also we're only going to be looking at this particular particle right here in the middle. What you have to realize is that all the particles in the area are going to affect all of the other particles in the area. Probably the best way I can explain that is you are familiar with the fact that the moon orbits the earth and that you've got the sun way far over here and that the earth is then orbiting the sun as well. Now, does that mean that since the moon is closer to the earth and it's orbiting, does that mean that the sun has no effect, no gravitational effect on the moon? Well, of course not. The sun has a gravitational effect on everything in our solar system. Okay, but the gravitational effect of the earth is much stronger on the moon than the sun is, just because it's that much closer. And so the earth is able to keep the earth in orbit around itself, and both of that system together is going to be in orbit around the sun. But they all have effects on one another because there's gravity between all of those massive bodies, just like we talked about when we talked about gravitational attraction. Okay, so if I look at this diagram up here, the particle on the left is going to have a force exerted on it by both this one and this charge, both of them. The particle on the right is going to have a force exerted on it not only by this one, but by this one over here as well. And so that could end up being one big complicated mess if I don't focus on one particle at a time. And the problem says, calculate the force on this particular particle. So that's what we're going to do. Okay, so if I look from the perspective of this particle in the middle, I'm going to look at this particle on the left first. I'm going to calculate the force between these 2 particles. So if I use Coulomb's law, my force is going to be K, which is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. The charge on these, the charge on this one, so it's going to be, remember we don't use signs here, 3.4 times 10 to the minus 3 coulombs. And then the charge on this one is 1.2 times 10 to the minus 3 coulombs. And I'm going to put that all over the distance between them, 1.2 meters. and that quantity is going to be squared, okay? So when I crunch that math out, I end up with 2.6 times 10 to the 4th newtons. Now, I have to stop and use my head to figure out what the direction is going to be. This is the magnitude of the force. If this is positive and this is negative, that obviously is going to be a negative number, but that doesn't necessarily mean the force is going to be to the left, which is traditionally what we've said, that left is negative and right is positive, because it depends on which charged particle I'm talking about. In this particular case, I am wanting to know what the charge or what the force is being exerted on this particle in the middle. So if we'll color code this so it makes it a little bit more clear. So this charge, or this force rather, this is a positive and this is a negative charge. We said that opposites attract, so they're going to be pulled toward one another. So if I'm looking at this particle, then I'm going to have a force exerted on this particle with a quantity of 2.6 times 10 to the 4th newtons. So it's going to be going off to the left as we have it drawn up here, okay? Now we need to look at this particle's effect on this center charge. So we need to do exactly the same thing. We're going to calculate that force. So I'm going to have K once again. I'm going to put the two charges in there, again without reference to any signs. And this one's going to be 4.1 times 10 to the minus 3 coulombs. And the distance between these two charges is 2 meters. And so that goes in the denominator and it is squared. So once I plug all those numbers through, I'm going to end up with 3.1 times 10 to the 4th newtons. So again, I need to do the same thing, and I need to figure out which direction this force is going. So we'll make this one green. And so here, because these are both negative, they are going to be repelling each other. So this particle is going to be shoving this particle further away from it. So that means that here again, what I have is a force that's going this direction exerted by that particle. So this is 3.1 times 10 to the 4th newtons. Okay? So both of these, this one exerts a force to the left on the center particle. This one also exerts a force to the left on the center particle, because these two are repulsive and these two are attractive. So you have to think through that in your head in order to determine which way that force is going to happen. Normally what we do is we say, well, if it's going to the left, it's negative. And so since both of these are going the same direction, they're both left, the total force is just going to be the sum of the other two forces. So I'm going to have, since this is going to the left, I'm now going to put a negative sign on it to indicate direction. So I'm going to have negative 2.6 times 10 to the 4th newtons plus a negative 3.1 times 10 to the 4th newtons. And when I add those together, that's going to give me a negative 5.7 times 10 to the 4th newtons. Now, what's the negative sign mean? Well, what it means is that it's 5.7 times 10 to the 4th newtons to the left. Okay? So that is going to the left, and that's what the negative sign means. I don't believe in this particular example that he actually puts the negative signs in there, but it is a technique that we are going to be using a little bit later on. You can see that what would happen up here is if this one happened to be going to the right, this would be negative and this one would be positive, and then the sign on the final answer would tell you which direction the net force was going to be acting. So it's not a bad idea to go ahead and get in the habit of putting the signs on here when you're calculating the total force we'll be doing something similar again for electric field later. So you want to make sure that on your final answer, you're always including the direction in that. Okay, so today's assignment is going to have only charges that are all in a straight line, and then tomorrow we're going to work on charges that aren't in a straight line.